All right. So let's keep trucking for a bit today. Just as a reminder, the next assignment is up on Blackboard. And it's due by midnight on Sunday like the other ones. So and then if you have not done the midterm, make sure you get that done this week as well. I know many of you have already done it, and those are graded and up already. So yeah, in any case, that's the scoop. So let's keep trucking and get through some stuff until about 9, and we'll call it quits. All right, so last time we were kind of talking about the kind of why do we want to network stuff, you know, as our computers got faster and faster, we found more and more ways of using our computers. You know, we decided, hey, we might want these guys to talk to each other. In the early days, maybe it was some file sharing, maybe it was sharing a single printer, you know, things like that, where we had external tools that we wanted to share among a computer. That then led to even larger computers being networked together. Maybe it doesn't take a huge step to say, well, maybe you know, an office building wants to share a central printer or something like that, or a central file server. Then it gets even bigger. Then we start thinking about, oh, well, what if we want to share resources across larger area networks? So kind of like that's where we get to this idea of a wide area network. So then what's the internet? The internet is just a supersized version of that. But we needed to have, you know, we kind of came up with an initial kind of services that the internet was going to provide. So typically when we think about the internet today, and I think that's represented on one of these slides here. Well, whatever. Whoa, Ninja. So on this slide, when we talk about the various applications, we start, you know, we're seeing some things about the internet here. So we have this idea of DNS, which we'll talk about today. Let me give myself a slide for it. I think we've already talked about HTTP at some point. That's our communication there. Oh, no, we really haven't. Then POP. So that's for email. POP is downloading email. SMTP is sending email. SSH is a secure shell, so talking to like a Unix computer. Before SSH, we might have used Telnet, and that would have given us access to something like this. We would have remoted into a computer and been able to you know, use that Unix system like this, and maybe if you were managing your files, you would have a home directory. And then your home directory, you might have some stuff that you know, use. So the idea of a secure shell allows you to have fairly powerful, even though it doesn't look graphically impressive, access to a remote computer. HTML, that's the language of the kind of the web. That'll be in our HTTP example. So effectively, what did we do? We came up with some core applications that we expect of the internet. And, you know, those change over time. You know, we, if you kind of think more recently, you know, most of you are, you know, at some point you've heard of a technology called BitTorrent. What can you tell me about BitTorrent? Anybody use BitTorrent can tell me about it?
It's a peer-to-peer connection. Uh, Anybody who is using a torrent, it makes a host like file sharing.
Okay.
Like 4 or 5 computers are using BitTorrent, so it interconnects through it and shares files through it.
Okay, so we have something called BitTorrent. So you said it's peer-to-peer,
Yeah.
where a bunch of computers can all be sharing the same files with each other, and each computer is contributing part of that file to the larger network. Let's say as needed. Why do we need this? So in this example, I'm kind of saying, BitTorrent was not something that was there in the early days of the internet. All right, so BitTorrent is something that's come into existence, I don't know, last 10 years or something like that. I lose track now, but significantly more recently than the early days of the internet. Why did we need something like this? Why did they invent it? What problem was it solving?
It's more efficient because as it uses there's a contribution part in it.
Okay, well, what do you mean by more efficient? How is it more efficient?
Like a bunch of computers are contributing for a single file, right? 20% from system A, 20% from system B. Whereas if without torrent, the file would come from a single source, so it would take a much longer time.
Okay, why? So the file coming from a single source would take a longer time. Why would it take a longer time?
The system of like the number of hops will increase, the packet hops.
So downloading from multiple sources will be, I'm just going to put it in quotes here, faster than downloading from a single source. So I'm going to say, why is that? And then we're going to remind ourselves. Remember that our download is the server we are downloading from's upload. A single server only has so much upload bandwidth. And if we have multiple users, people are still joining. We have multiple users all trying to download from that single source. The bandwidth will be shared, and the users may not maximize their download speed. All right, so if you're downloading from a single source, and you're trying to use the maximum potential of your internet speed. So if you have 200 megabits per second, and the place you're downloading from can only serve you the file at 10 megabits per second, the fastest you're going to download it is 10 megabits per second. And that's if you're the only one downloading. If you're one of 3 people downloading, you're only going to get 3.3 megabits per second. All right, so downloading from a single source has the limitation of them running out of bandwidth. Pretty similar to if in your apartment or your house, you have the city water or whatever coming to your house. and it comes in with a certain water pressure and a certain amount of water that's available. And if too many people are using water in the house at the same time, if everybody turns on every faucet, everybody turns on every shower, there's a decent chance there's going to be a drop off in water pressure, because you're trying to use the water faster than it can give you the water, something like that. All right, so the idea here with BitTorrent is, well, as our internet connections keep getting faster and faster and faster, we might want to come closer to using the full speed of our internet connections. We had talked about why have fast internet connections earlier, and had decided that, okay, well, fast internet connections is maybe it's so that multiple people in the house can use the internet at the same time doing different tasks, and they're all pulling from that same using the metaphor, that same water source. All right, so if we want to come up with a way of better maximizing our download speed of our internet connection, we could download our files from different sources. So maybe we have, if we download half of a file from one source and half of a file from another source, presumably we would get the maximum download speed that is the upload speed of both of those sources added together. Now, if you keep duplicating that, you keep getting more and more benefit from it. Now, at the same time, you then also end up participating in that mesh network. So while you're downloading from some sources, you also provide some of the parts of the file that you've already downloaded. Excuse me. You're providing them as upload to other people interested in download. All right, so that's the concept of BitTorrent. So this was something that was not there in the early days of the internet, but we would say is a internet application. Now, BitTorrent has, over the years, gotten kind of a bad name for itself, right? Keeping in mind that BitTorrent is the underlying technology. You're still at the mercy of what the end users are choosing to share over BitTorrent. So BitTorrent tends to be a a source for a lot of like illegal downloads, movies, ripped movies, things like that you probably should be paying for, and that kind of stuff. But the BitTorrent technology is also now heavily used for like software updates, whether it's a video game or an operating system update, things like that, where, even if you have a big company like Microsoft, for example, giving a software update, presumably Microsoft has more upload bandwidth than most companies, right? But it's still not an unlimited amount of network bandwidth. And when you consider the number of users who are going to be the recipients of that upload, of that software update, that bandwidth is going to go away pretty soon. So what do some of these big companies do? Well, they take a couple of different approaches. First of all, they stagger who gets the updates. So not everybody's getting it at the exact same time, but then they're also using technologies based on BitTorrent to spread the wealth of how those files are being downloaded. All right, so you see that BitTorrent here isn't one of the examples they use here. It wasn't there in the early days of the internet, but it's certainly a technology that we rely on for the internet today. Similarly, some of the technology around data compression and video streaming and stuff like that, these were protocols that didn't necessarily exist in the early days, but that we've built on top of the idea of the internet. And now when we say we built it on top of the internet, what we're really saying is we live with our computer connected to the internet, we live in a giant computer network. And now we can use our imagination to decide what types of things might we want to do, what might we want to communicate between these computers. All of us right now, we're on a Zoom call. So Zoom didn't exist in the early days of the internet. There probably wasn't enough bandwidth to do, certainly not video, but even audio. Having that many people in a room was going to probably break up the connection and things like that. But now it's become something that's very, very commonplace. I even just think about the ridiculousness of it today relative to 20 years ago. I'm sitting in my office at the school right now. Nobody else is here yet. And, I have my door shut. I'm just in my room talking to myself, when the reality is I have an audience of 18 people that I'm speaking to, and you guys are all sitting wherever you're sitting, probably in your living room or your office, or probably maybe still in bed, whatever the situation is. And that's been a technology that we decided, hey, we now have the bandwidth to support this kind of thing. Let's go and do it. So kind of the sky's the limit. Our imagination is what drives how we choose to use those networks. So back to this slide of why networking. It's because we want to share stuff between computers. And our idea of what are the things that we might want to share or the applications we might want to do are going to continually shift. I see this kind of taking even a bigger step. So let me switch over here. I'll just get up. Let's see. Let's do Meta workspaces. So now we're starting to see things in, what's it called? Workspaces or workrooms? Workrooms. Yeah, so something like this. So, now virtual reality is starting to become a major thing. And, I have a headset sitting here right next to my desk, and I do a lot of VR meetings with students and with other companies and things like that. The department here tends to be, we're very VR centric. So we do software development in VR and things like that. And, for any of you in here used virtual reality before? And what have you used?
For movies.
Okay, so what device? Or do you
It's
just
like,
use your phone with one of the headsets?
yes,
for your phone?
yes,
Okay.
something like that only.
Yep. Anybody use any of so movies? Watching movies is a good use of VR. I do that with several of my students. Will because in VR it changes your perspective. So we're all sitting in our house, but we're joined together in a movie theater, and it looks like a real movie theater. You feel like you're looking at it on a 100-foot screen, and we're watching movies using an app called Big Screen. What other devices have people used? Any of you use like the Oculus Rift, the HTC Vive? I don't know what's like readily available in India, or what you've been exposed to here. No other devices. Fascinating. So, next time you're on campus, we have about 20 VR headsets here on campus. And the ones we're mostly using now are the Oculus Quest 2s, that's the current flagship VR headset. We also have a couple Valve Indexes, which are considered to be the highest end gaming ones, but the Quest 2 is the better headset. That's my main everyday headset, is the Quest 2. So I strongly encourage you to come and check it out, because you're missing out on a whole part of communication technology that you maybe have seen before. So like in this picture here, this application from Meta, Facebook, is called Workrooms, and it allows you to have, I think it's up to like 25 people in the room at once. You can have a couple of different room configurations. So this is kind of the presentation thing. Well, each of these people are a person sitting at their couch or whatever, connected to Workrooms. Here's a different orientation. This is the one we use pretty often. I run a VR think tank on Saturday mornings with a research group, because we're operating off of a $250,000 grant from Facebook for research and development for VR. So we all have a Quest 2 headset, and we have our avatars configured, and we just put the headset on, and we're immediately in this group where all of us with headsets are sitting here as avatars, and we can turn and talk to each other. You can see who you're paying attention to. It really mimics the way real life works, much more so than like a Zoom meeting like this. But notice here on the back wall, these are people who are joining this meeting via effectively like Zoom. So they're joining from their laptops. Now, I would say they effectively end up becoming second-class citizens in the room, because it's not the same experience, but they're still, part of the conversation. There's also kind of a boardroom setup for it. You can do screen sharing. You can have your computer monitor linked in there. You can use your computer inside of VR. So you can be sitting at your desk, even using workrooms. You don't have to have a meeting with multiple people. You can just go in with your normal desk and have your computer screen pop up, and you can do it in this size, or you can make it, I would say it's a roughly equivalent to about a 40-inch monitor. And I actually use that pretty often in coffee shops. So I bring my MacBook Air, which is a 13-inch screen, with me to a coffee shop along with my VR headset. And I'll sit down and I'll put my headset on, and I'm now using my 13-inch MacBook Air as if it's a 40-inch screen in the middle of a coffee shop. Just kind of fascinating uses of technology. And there's a couple of other competing technologies with this. Another one's called Spatial that also uses VR, but this is going to be something that's going to become more and more prevalent over the next several years. So if you haven't done anything with VR, I strongly encourage you to take advantage of the resources we have here on campus, and set up a time to come in. You can shoot me an email. We can set up a time for you to come in and mess around with it. We don't just have the business applications, we have games. So you can try all the different famous games, Beat Saber, stuff like that. So we're pretty up on it. But in any case, these are other ways of doing network communication that are trying to mimic the real world. And this has actually become a pretty major thing during COVID, right? When we've all been locked inside. You can still get out and do things, and VR is allowing us to do stuff that we couldn't even accomplish before. For example, my dad lives 4 hours away or so it's not a huge amount of time, but we don't see each other in person all that often. But I sent him a Quest 2 headset, and we're both basketball fans, so we'll meet in VR at least a couple times a month, usually about once a week, in an app called Horizon Venues, where we can go in and Horizon Venues. So when you go into Horizon Venues, you're basically in a room that has a whole bunch of like entrances to movie theaters. And you can go into one of those theaters. Let me just see if they have a thing for the NBA. I think this is actually one of the views. Yeah, so for example, if you're in Horizon Venues, you could be watching a professional basketball game like this. And the view changes depending on who has the ball and things like that. So you're like sitting under the basket. You better seats than you could ever buy at the at the arena. Even if you had unlimited money, better than floor seats. So it's actually pretty amazing. And you see the the halftime shows and all that stuff, and it doesn't cost you anything. I'm sure eventually they're going to start charging for that kind of stuff. But the point is that so here's like an example. If you're you in there, you can subscribe, to one of the games, doesn't cost you anything. It'll send you a reminder, and you can go and watch, these different sporting events in VR with people that but who aren't sitting right next to you. And it really is kind of an amazing type of experience. And those things are going to become more and more prevalent. But there's an example there of network use. So, when you start thinking about powering all these avatars and things like that, that's going to require the device you're currently using, whether it's your computer or your headset. The Quest 2 is a standalone headset, so you don't even need a computer to do the stuff I'm talking about. All you need is the headset. It doesn't use your phone either. It's completely self-contained. And it's like $300 now. So, not incredibly expensive. I realize for poor college students, that still is pretty expensive, but it's way less than it used to be. But the idea is that all the heavy lifting of the graphics and stuff like that, that's done on the headset or done on your computer if you're using a PC connected VR device. So that's not stuff that needs to be transmitted over the network. What's actually being transmitted over the network is, like in an NBA game, is the video signal, that type of thing. So it's effectively applying something we've already been doing for a while, and that is, video streaming. And the signal we're streaming is actually a virtual reality capture, a 360 video instead of a flat screen video or 180 video. Most of the sports stuff are 180 degree videos. Streaming takes a little bit less data. You're only showing half of the kind of the sphere that you're in, where you're on the back wall and you can see everything that's kind of in front of you. But these are things that we're starting to use our network connectivity to accomplish, and now every single year they keep doubling our resolution, right? You got 4K, 8K, 12K, some of these, if you go into YouTube VR, you can do it on even your computer. So if you do YouTube, and let's do 360 India tour. Yeah, so here's a 360 degree video of a tour of Bombay. Let's see, are any of them, this is a year ago, it's probably at least in 4K. So if I start playing that, you can see I can turn the camera around. Now, if I was in a VR headset, I could just turn around physically and look all around me, and I can look up and, and all these things. I'm the one controlling what I'm looking at here. So imagine putting a VR headset on and being able to go and visit all these places all over the world, just from your apartment. It's really it's an amazing technology that's going to be the future. So I encourage you to, when you're on campus, to check out the headsets and kind of see what it's all about. And like I said, send me an email and we can set something up for you to come in and try it if you just want to make sure the headset's available when you're on campus, if you're not here every day or something. So in any case, we're really talking about different applications of the internet. What are the reasons why we might want to have multiple computers that are spread all over the place talking to each other? Now, in the early days, we had a very small subset of computers, or we had a small subset of technologies that we thought, hey, this would make sense. For instance, usually when you think of the internet, you think of web pages. That's kind of your starting point. Or you think about email. So in the early days, we probably had email, we probably had web pages, and FTP was something else that was common in the early days, where you could transfer files between computers. Something like that. But typically web pages and email are probably your sweet spot for how the average consumer used the internet, with the heavy emphasis on web pages. Anybody who used the internet in the early days did it for web pages. All right. So we talked last time about the idea of this thing called TCP TCP/IP. Pretty sure we talked about that, right? Yeah. So we were talking about the Ethernet protocol and how the Ethernet protocol uses a bus-based system where the things that are traveling over the cable could collide with each other, causing corruption. And TCP/IP, TCP is the protocol to allow us to recover from those issues. And that's what this picture shows, is the compressed TCP model over the OSI model. And really it just says, here's the layers that occur when data is being sent or received. And TCP, that idea says, we're going to monitor the data and make sure it actually arrives, and we will resend if necessary. That's kind of the idea of TCP. So there's two different, let's call it sub protocols of TCP. One's called TCP, the other one's called UDP. Now TCP will resend data packets when corruption occurs. Used for file transfers where it is important that the arriving data is intact. UDP will not resend data packets when corruption occurs. Used for video streaming, for example, where one dropped frame isn't a huge deal, and pausing the video to resend a single frame would be annoying. All right, so also UDP is used in video game communication. You know, we talked about you know, near the beginning of the course, kind of some of the video games where they're doing real-time communication. And you know, if you've missed the opportunity, especially like these first-person shooters where everything's moving so fast, if some data was lost that, you know, you shot or you moved one pixel over, you know, that's in the past now. Resending that's not going to help us. So UDP just keep sending data with the assumption that some corruption might occur, but the idea that it's real-time streaming, that the actual experience should fill in those gaps, because a lot of times it's going to be, you know, just a little bit of data that's off, or one frame that's dropped out of, you know, 240 frames being shown in a single second, that kind of stuff. All right. So that's the idea of the TCP part of that. Now we have the idea of the IP part of that. Okay, so IP is our is where we get our internet addresses. Oh. This is a unique address assigned to a computer on a network. Now this gets a little bit interesting when we say unique address assigned to a computer on a network. So the original was something called IPv4, and IPv4 was 8 bits, followed by 8 bits, followed by 8 bits, followed by 8 bits. So you may have seen an address like 172.22.231.7, something like that. That would be like an IP address you may have seen. So this value is an 8-bit value, so some number between 0 and 255. You know, we talked about the range of values with binary, right? So if you have 8 bits, you can represent 256 unique numbers. All right. So in IPv6, those are 16-bit values. Okay. So one thing we might say here is if we have 256 unique values that can go here, and 256 unique values that can go here, and 256 unique values that can go here, and 256 unique values that can go there, we have 256 times 256 times 256 times 256, which is, and that's 32 bits total, right? So that's 4.29 billion. So I'll copy this. Okay, so we have 4.3 billion unique IP addresses. How many computers are on the internet at one time? See if we can get a real number. It doesn't look like we're going to get any sort of statistic for that. Okay. But when you consider all the people in the world who have internet access, and you consider the number of devices that each of those people might have, and you consider the number of businesses in the world who also have devices connected to the network, is it plausible that more than this number of devices are connected to the internet at one time that need to have a unique IP address? That's plausible, right? So we might say we are running out of IP addresses. Now, we're going to throw this in there because many devices are trying to connect to the internet at once, as well as the way we distributed IP addresses was by assigning internet nodes, usually companies, a block of IP addresses based on their, let's say, based on the number of computers they had. Okay, so in the early days of the internet, the idea was every single computer was on the internet. When you connected, you got a real IP address. Routable versus non-routable IPs. So in the early days, all IP addresses were routable. This means they were unique on the entire internet. All right. Now, what computers actually need to have routable IP addresses on the internet? These are the computers that might serve as hosts, that might be, acting as servers on the internet, giving data to other people. Now, this gets a little bit wonky with BitTorrent. That's where the peer-to-peer stuff comes in. So we have to have some way of allowing that to happen. We'll draw some pictures here, either in a little bit here or on Monday. But the reality is only the computers that are actually the entry point to the internet from these different companies that live on the internet, for example, only those need to have unique IP addresses. So only, we're going to say the servers or initial entry points onto the internet need to have a real IP address. Non-routable IPs are addresses that are unique among the computers on the smaller network with that network's connecting point to the next larger network having a unique IP on that network as well. And if we kind of draw a picture of that, let me see if I can. I think this will work for my. Let's see which one's going to let me show what I was just showing a router. Yeah, this actually isn't a bad one. All right, so in this example, and it can go more layers than this, but in this example, the internet lives out here. So we have a single device. If we're thinking about it from our house, we have a single device in our house that is our link to the internet. Now, keep in mind, there might actually be another network in between here. So there's no guarantee that your home router, probably like your cable modem, there's no guarantee that's getting a routable IP address. That might be given a non-routable IP address by another network that lives in between here. Okay. But the idea here is that the internet lives out here. Only this device has to have a unique IP address among the stuff that's out here. These devices only have to have unique IP addresses among themselves. So this computer, this computer right here, this gaming console, this guy can have the identical IP address to your friend's laptop over in their house that has their own home router. It only needs to be unique among their network. And then their connection point to the internet needs to have a unique IP address. So this guy right here actually has two what are called network interface cards in it. So if you look at the back of your cable modem, let me get a better picture than that. Well, this will get the job done, I guess. All right, so here's the back of your cable modem here. Your connection to the internet, or your connection to the next larger network, this piece out here, that guy's coming in over this coaxial cable right here. So that's what comes from the wall to your cable modem. Then you can have other computers. So this guy only has three other ports. Some of them have larger ports. This one has 4, for example. But then, so this guy has one connection to the internet and then another connection feeding these internal guys. So off that cable modem, what we would have seen if this guy only had 3 ports on him, one port's being used here, another port's being used here. Those are feeding into a network switch, which basically lets that one port act like, I don't know, probably 4, 8, 16 ports. So when this printer connects to that switch, this desktop, this laptop, whatever, these guys connect to that switch. They are then talking to that single port up here through this switch, just like these guys talk through this switch to this single port. So we're only using 2 ports here, even though we might have 16 ports available to these computers in here, maybe 8 per switch if it's an 8-port switch. So these guys just have to be unique among each other. Okay, so everything that's inside this network here has to be uniquely identifiable by an IP address. But that IP address can come from different sources. So chances are, notice this guy says it's a router. So we've heard that term before. So a lot of times you'll hear it like in a Wi-Fi router or, well, might be most common for us, but a cable modem also acts as a router, and then there are all sorts of various size and capability routers out there. All right, but ultimately the job of a router is this. A router has one port that connects it to a larger network. A router has many ports, so usually 4 or 8 or 16, yada, yada, yada. The more extra ports that are on a router, typically the more expensive that router is. And that's not just because it's more ports. That's also because that router has to have a larger computing power within it to manage that many machines all utilizing that router at once. All right. What does a router do? So we can actually think about this from if you've ever been driving or in a car and run into one of these situations where maybe the stoplights are not working, right? And you have a person out there who's kind of controlling traffic, right? They're telling, one person to stop, they're telling another person they can go, things like that. So that would be kind of a manual version of routing. They are routing those vehicles, making sure that everybody's behaving so that there aren't car crashes and things like that. On a more automated level, we have traffic lights. Traffic lights handle routing, right? They let cars flowing in one direction go for a while, then they stop them. They let cars in another direction go for a while. It's a form of routing, okay? So what does a router actually do? It manages multiple computers talking to each other within the network that the router connects to the larger network, as well as routing data on behalf of the internal machines to and from the larger network. All right, so that's what a router ultimately does. A router is our connection point, for instance, to the internet. All of these computers want to use the internet. So when this desktop says, go to google.com, it's going to send that request through this router. That router is going to make the request for that computer, receive the response, and then route it back to the person who requested it. That's what a router does. Okay, and there's different routing algorithms and things like that that manage all those things. But at the end of the day, that's what a router does. What is a common name for, well, here, I'll just ask it out loud. So we're talking about it from a network equipment perspective. That's what a router does. But commonly, routers also serve the purpose of something called a firewall. Okay, what's a firewall? What's the purpose of a firewall? And you can think about this in real life or in computing. I'm asking the computing version of it, but I'm going to use an example of real life. So when we think about a piece of hardware that's a firewall, if I say that this guy here is a firewall, it's a router in terms of its capability, but it's also acting as a firewall. What is it doing?
It secures the network.
Protecting other.
It's protecting the network from external invasions.
Okay, so this guy right here, if he's acting as a firewall, he is protecting all of these guys from connections coming into the network from the internet in this picture. All right, so this desktop right here, if they have you know, some shared files, maybe it's your tax documents. Well, this guy acting as a firewall is preventing external observers to get into your network and ultimately browse that person's files. Now, we have something on our computers called ports. So this guy protects the internal computers from external it's just the external viewing. We're going to say across multiple ports. What is a port? Let's put it on a so a port is a communication channel on a computer that is managed by the computer's OS. Common applications which run on certain ports. So for instance, the web, which is HTTP. Anybody know what the default port is for a web server?
Port 80.
What did you say? Oh, port 80. Yep. So it's port 80. So typically, so if I'm on a web browser here and I go to www.google.com like that, I'm actually going to port 80 at that address. All right. So when I just type in google.com, it's automatically appending port 80 there. But if I say go to port 7272, I'm just making up a port and I press enter. It's still trying to connect. Google's blocking us on that port. That's not a legal port on Google's web server. Okay, so those individual ports live on an individual computer. So a computer can say, we are offering multiple external services, although a port can be used internally as well. But typically when we think about a port, it's how do we allow aspects of the services provided by this computer to be accessible by things outside of this computer. And we can divide those up among individual ports. Now, the number of ports that are available on a computer are going to be governed. So how many ports does a computer have? These are not physical ports. So this is governed by an integer of some size. So we might say perhaps 16 bits. Which would give us 65,536 unique ports. Okay. So that's if it's a 16-bit number that's representing our ports. So port 0 to port 65,535. That means we have 65,536 possible unique communication channels that a computer who's managing their ports through a 16-bit number might be able to communicate over. The next step down would be an 8-bit number, which gives us 256 unique ports. Now, we could make the argument, is 256 unique ports enough? Well, practically, maybe. Maybe that actually is enough for the obvious applications, but ports are also used internally on a computer for communication between applications. So having more than 256 unique ports might be handy. So our next option up, you can't just say, well, it's going to be 300 ports. Our next option up is to give ourselves a bit space that can store 65,536 unique ports. So we're going to use 16 bits, the next power of 2. Okay. So I would say that's probably a fairly common number for the number of ports. And a lot of times the first 1,024 ports are kind of reserved for the kind of common operating system, or like for instance, port 80 is within that first 1,024 ports. It's already been flagged as a known port, a port that has a common use already. So if we do a search here, internet ports on a computer, it'll show us like port 23 is TCP. Port 20, port 21 is for FTP, port 22 is SSH, port 25 is the send for email, port 53 is for DNS, we'll talk about DNS, port 80 is for the web, port 23 is for telnet. This probably gives a broader list somewhere. Port 123, network time protocol. Port 443 is for secure HTTP. Now, interestingly enough, outside of those first 1,024 ports, notice that port 3389 is what's used for remote desktop protocol. So this was a protocol that came out later. And when they wrote that third-party application, remote desktop is something that you install on your computer after the fact and doesn't require hooks into the operating system. It's using a port outside of those first 1,024. Here's the full list of port numbers. So you can see here, these are the ports, and some of these are, you notice, just make this a little bit bigger. Some of these are internal computers talking to each other, internal programs talking to each other. Oh, there's a zillion pages of it and stuff. All right, so those are our ports on our computer. That's what we're talking about when we're talking about ports on a computer. So one thing a router can do is a router can say, we're going to block a firewall, which typically is on a router. So firewall would be security software running on a router, usually on something called an edge router. That is the router that's sitting at the edge of the network between that that network and the external larger network. Because internally here, we could have other routers. You could have multiple routers on a network. In fact, probably at home you do. At home, you probably have your cable modem, and then one of the wires from your cable modem is plugged into your wireless router, which is giving wireless network access to the computers, your wireless devices in the house. And then maybe you have another solid cable going from your cable modem to your, potentially from your cable modem directly to like your Xbox or your PlayStation or something, and giving that guy wired access to the network. You could do that through the cable modem directly if it has multiple ports on it, or you might plug it into your Wi-Fi router. But the point is you can have multiple routers inside of a network, and typically the edge router, the one that's actually sitting between that network and the external world, whatever that is. If the next level up is the internet, that's fine. If the next level up is just a larger network, that's fine. But that firewall, it can provide services like allowing individual connections to come in. So for instance, this desktop computer right here, maybe you decide, you know what, I want to run a web server on this desktop computer. So what I'm going to do is I'm going to go ahead and I'm going to have a piece of software running on port 80, a web server, an HTTP server. But the problem is that this guy probably has a non-routable IP address. So he doesn't have an IP address that's unique to the entire internet. He has an IP address that's only unique inside this network. So how do people out here on the internet get to this guy? And that's done through something called port forwarding. So somebody would actually connect to the IP address. Let's assume it's a routable IP address on this router. And then this on port 80. And then this router say, oh, somebody's trying to talk to me on port 80. I need to forward that to this internal computer's port 80 and actually have him serve that request. And when he gives his answer, he'll send it back to me and I'll forward it back onto this guy. Okay, so that's the idea of port forwarding. So we can have a firewall by default block all incoming connections, and then we can poke individual holes in it to allow certain internal services to be available externally. So the next thing we'll talk about on Monday is the net. We already talked about port forwarding. Let's say port forwarding allows for individual services to be accessible inside the network by making exceptions in the firewall. So the next thing we talk about is a NAT, which is how that router works internally. Then we'll talk about DNS, how ultimately things work on the internet. Okay, I think that's a decent stopping point. All right, so any questions, comments, concerns, bribes about any of this stuff we talked about today? Nothing? Okay. So make sure you get the midterm done before midnight on Sunday. You also get the assignment in by midnight on Sunday. And I will see everybody on back here on Zoom on Monday.
Awesome. Thank you.
Thank you.
All right.
Okay.
Have a good
Thank
one.
you.
Thank
You too.
Thank you, Dr.